Hey everybody, Dr. A here, and in this video we are exploring a second example of axial deformation, and this one is more of a calculation type of example, not a derivation like our first example was. So let's take a look here. In the given information, we are being told to compute the axial deformation of the free end of this system with respect to the fixed end due to the applied loads. And so here's our given diagram. Notice we have a 3-segment axially loaded bar system. We have a segment AB here. We have another segment BC, and then at the end we have this attached segment CD. Up here at the top at point A, you have the fixed connection, and then at point D, that's our free connection, okay? We also have applied loads. Notice at the interface at point B, between the first and second segments, we have a downward oriented 1.2 kip force. At the interface at C, between the second and third segments, we have an upward facing force of 0.5 kips, and then down here at the free end, you have, at point D, you have an upward facing 0.2 kips. We also have the lengths of each of these segments. Segment AB is 12 inches long, BC is 8 inches long, CD is 6 inches long, and then each of these segments has their own cross-section area and modulus of elasticity labeled with subscripts 1, 2, and 3. Referring to the first, second, and third segments, okay? So let's go ahead, maybe pause the video, write this down, and make sure you know what you're looking at, all right? And we can go ahead and start with our solution. So since this is a segmented axially loaded system, we know we're going to need to use the summation version of this equation. And not only that, but we're going to have a summation of constant values, okay? So we're going to say summation from I equals 1 to 3. Here, 3, we're using 3 because we have 3 segments of PL over AE sub I, okay? So if we expand this summation, what we'll really have is P1L1 over A1E1 plus P2L2 over A2E2 plus P3L3 over A3E3. So again, you can expand this summation into its 3 terms. Again, 1 term for each segment. So we just need to be organized and make sure we know what we're looking at. This first term is segment AB, the second term is segment BC, and the third term is going to involve segment CD, okay? And so really what we need to do is determine what all of these values are so we can build it together and calculate this deformation. So again, you know, I like, when I start problems like this, I like to start with my governing equation, because if you start with your governing equation at the onset of the problem, then you can more clearly see what you end up needing to calculate along the way, all right? So let's ask ourselves this question. Do we know some of these values in this expanded equation? Well, yeah, absolutely. So I'm going to check off in yellow what we already know. We know the 3 lengths, right? We know that L1 is 12 inches, L2 is 8 inches, L3 is 6 inches. So I'm going to put a little check mark by L1, 2, and 3 because I know them. Do I know each of these segments' cross-section areas and moduli of elasticity? Absolutely. All that was given in the problem statement. So I just need to make sure I substitute them in properly, but I know them all. I know A1, A2, and A3, and I know E1, E2, and E3. All of these were given. So the question is, what do we need to find out about P1, P2, and P3? These are the 3 remaining terms that we currently don't know. P1, P2, and P3. Now, you may be looking at this and you may be saying to yourself, oh, wait a second, I know them. P1 is 1.2 kips, P2 is 0.5 kips, P3 is 0.2 kips, and I'm done. I know everything. If you do that, you're making a mistake. That's a fundamental mistake. Remember, the p-values are internal axial forces, okay? So p, quote-unquote, p-values are internal axial normal forces, okay? Not the applied loads. So what you need to ask yourself is how do I get these internal axial normal forces? Okay, what you need to do is use method of sections to get P1, P2, and P3, okay? So method of sections, if you remember, that's a technique that you should have learned in a statics environment, a statics course of some sort, and that's where you pass a non-real cut plane through a member at a particular location, and then you apply equilibrium equations to find what the internal loadings are where you place that cut plane. So I'm going to go through that, and if you're a little rusty on it, that'll be a good review. So let's go ahead and calculate P1, okay? Calculate P1, okay? This is inside segment AB, okay? So what I'm going to do is I'm going to make a cut section inside segment AB, okay? Somewhere inside segment AB. And then I'm going to sketch everything that is on one side of that cut section. So in this case, I'm going to sketch everything that's below that cut section. When I do that, the thing that is becoming exposed here at that cut section is P1, okay? So this right here is my cut section, all right? Now, when you draw this, we're going to say, we're going to call this a free body diagram of cut section in segment AB, okay? And so remember, with your free body diagrams, you need to go ahead and sketch all of your known and unknown values. So we know that this length is 8 inches. We know this length is, the bottom length is 6 inches, okay? Now, what else do we know when we look at this free body diagram? Well, we know some of these applied loads, right? Look at our original figure. We know that we have 1.2 kips, 0.5 kips, and 0.2 kips. So again, this cut section is passing somewhere in between this segment AB right here, and then I'm looking at everything below the cut section, okay? So again, you need to draw these known values. Here's our 1.2 kips that we know, here's our 0.5 kips that we know, and here's our 0.2 kips. All of this was given to us in our problem statement. So at this stage, what we're going to do is we're going to look at this free body diagram, apply force equilibrium in the vertical direction to solve for P1, all right? So here's what I'm going to do. I'm going to say sum of the forces in the y direction equals 0. Typically, we call things pointing up positive. So I'm going to have a P1 minus 1.2 kips plus 0.5 kips, and then plus 0.2 kips, all equals 0. I can rearrange this, and I'm getting out my TI-36X Pro calculator. And of course, we rearrange this and we get 1.2 minus 0.5 minus 0.2. And so I get 0.5 kips. And this thing comes out positive, which means it is in fact pointing up. And if you recall from a statics environment, whenever you have an unknown force that's calculated as pointing away from the cut section, that is a tensile effect. So we can say 0.5 kips with a T for tension there, okay? So that's step one. There's P1, okay? Notice that is not, P1 is not 1.2, okay? It's the internal load that you obtain by using method of sections in the segment of interest. So let's do this again. We got to do this 2 more times, once for each of these segments, once for each domain, okay? So now I'm going to say free body diagram of cut in section BC. So in a similar way, I'm going to make a cut section, but this time my cut section is inside of BC, inside of that middle segment, okay? And I'm going to, remember from method of sections, you need to draw everything in a free body diagram that is on one side of the cut. So here I'm basically putting a cut section through BC, and I'm drawing everything below that cut section, all right? So what is below that cut section? Well, you have this little 6-inch segment, and you know that you have 0.5 kips here, and we have 0.2 kips here, and then this is P2, okay? Now, why is the 1.2 kips not showing up in this free body diagram? Well, remember, method of sections, if you're cutting through this middle segment BC, and you're looking at this bottom portion free body diagram, the 1.2 kips is not in that free body diagram. It's above that cut section, so that's why it's not showing up here, okay? So now we're ready. We're going to follow the same process. Sum of the forces in the y direction equals 0, and we're going to have a P2 plus a 0.5 kips plus a 0.2 kips equals 0. We get P2 equals negative 0.7 kips. So what that negative means is the 0.7 kips is actually pointing in the opposite direction of what we assumed in our free body diagram. So the negative will indicate that this 0.7 kips is actually pointing down. And if you also remember from statics, if you have a force that is calculated as pointing into the cut, then that is a compressive force. So P2 is going to be 0.7 kips in compression, okay? Last step, we're going to do this one more time, but for CD. So we're going to say free body diagram of cut section CD, and we're just going to make a cut through that last little segment CD. And what is going to show up there? Well, only the 0.2 kips, okay? And coming out of the cut, we have this unknown P3, and so by equilibrium, you should be able to see that, you know, if you say sum of the forces in the y direction equals 0, you can say P3 plus 0.2 kips equals 0, P3 equals negative 0.2 kips. Again, the negative means that this P3 is actually pointing downwards, so 0.2 kips pointing down, which is into the cut, so P3 is 0.2 kips in compression, okay? So these are our three internal forces. Let's summarize them. P1 was 0.5 kips in tension. P2 was 0.7 kips in compression. And P3 is right here, 0.2 kips also in compression, okay? So just to kind of remind you, these steps right here are not actually mechanics of materials steps. These steps that we just went through in calculating P1, P2, P3, it's really static steps. It's really from a statics course, not a mechanics of materials course. Method of sections is a static equilibrium technique, not really a mechanics of materials technique. Now, calculating the deformation of point D is a mech of materials technique. So the deformation at point D, again, it's P1 L1 over A1 E1 plus P2 L2 over A2 E2 plus P3 L3 over A3 E3. And so now we have all of these values and we're ready to substitute them in. Make sure you're careful wherever you have a compressive internal force that needs to manifest itself as a negative sign somewhere. So let's substitute these in. We're going to have 0.5 kips times 12 inches, all divided by A1 and E1. These were given to us in the problem statement, 8 square inches and 29,000 KSI. So we're going to come down here and substitute that in, 8 square inches and 29,000 KSI. Check those units, make sure we have consistent units, plus negative 0.7 kips. That negative is manifesting itself because that's a compressive effect, times 8 inches, all divided by A2 E2, again, given in the problem statement, 5 square inches and 17,000 KSI. So scroll back down here, 5 square inches, 17,000 KSI, and then plus minus 0.2 kips, again, a compressive load, times 6 inches divided by A3 E3. That's 2 square inches and 10,000 KSI. 2 square inches, 10,000 KSI. Now I'm gonna crank this through in my calculator. Again, I got a TI 80, not TI 80, TI 36X Pro. Again, fantastic calculator. So I'm gonna punch these in one at a time just to be safe. 0.5 times 12 divided by 8 divided by 29,000. And so this first term comes out to be 0.00002586 inches. Check those units. Track your units, people, okay? You've got square inches times kips per square inch. So you see the square inches cancel in the numerator, then the kips down in the, the square inches cancel in the denominator, and then the kips cancel with the kips in the numerator, and so you're just left with units of inches finally, okay? So track your units. Pause the video, make sure your units make sense, okay? Second term, we have a 0.7 times 8 divided by 5 divided by 17,000. And so here we get this negative term, since it's a compressive effect, of 0.00006588 inches, okay? And then the last term, 0.2 times 6 divided by 2 divided by 10,000. And so again, we get a negative number here due to the compressive effect, 0.00006 inches. And so we add all these up. I'm punching all these through my calculator. Be patient when you're punching these in your calculator. Don't try to be a hero and crank them all in at once. That could be a recipe for disaster. And then minus 0.00006. And so I get a negative 0.0001 inches. And so what this means is you have a contraction effect, okay? So this is 0.0001 inches in contraction. So what that means is point D will move up, okay? Point D is going to contract upwards. So for example, if this is our quick sketch of our original system, okay, quick sketch of our original system, and this is point D, and you know, we had these loads on here. We had, what did we have here? 1.5 kips, 0.5 kips, and I think this was 0.2 kips. Make sure that I'm writing the right loads here. 1.2 kips was the first one, I'm sorry. 1.2 kips was our first load. Then what's happening is this point D right here is actually moving upwards, okay? So the deformed shape of this would show point D actually moving upwards here, okay, by an amount 0.0001 inches due to this applied loading, okay? So that's just kind of a little graphical representation of what what's happening. Point D is moving, is contracting due to the compressive effects are overwhelming the tensile effects in this system. So that is the conclusion of this example. Thanks for watching. Please hit like and subscribe.